Hello, this is Jack Jackson. We're going to compare a summary comparison of Euclidean hyperbolic, spherical, and taxicab geometry and some of their properties. Now, certainly there are students who may want to just study Euclidean geometry, or at least mostly study Euclidean geometry, and many of my videos in these playlists can be used for that purpose, for example, in a high school class. But if you've been following all of my videos, like my college geometry students, you will see that we have been studying Euclidean, hyperbolic, spherical, and taxicab geometries simultaneously throughout most of the semester thus far. And while all four geometries can be considered equally valid in some way, and they are each practical in certain real-world application, one of the main reasons why we have studied all four geometries is to gain a deeper understanding of what postulates are needed to deduce certain properties. For example, the main reason for studying taxicab geometry is to see that the SAS postulate is independent of the other postulates in Euclidean geometry. It gives us a better insight into Euclidean geometry. And the main reason for studying spherical geometry, and especially hyperbolic geometry, is to see that the parallel postulate is independent of the other postulates in Euclidean geometry. That one is of particular historical importance because that was a big deal historically in the history of mathematics when that was discovered and when people started realizing the ramifications of that. It actually transformed a lot of the way we look at mathematics. So I have a rather large table here we're going to go through, giving a side-by-side comparison and contrast among the four geometries. Earlier, we introduced a portion of this table. This one's expanded to include some information we've studied since then, and we're even going to include a row or two of some material that extends beyond our study this far. Okay, now there are multiple models for the hyperbolic geometry. I'm going to be using the one I've been talking about all semester, the Beltrami-Poincaré half-plane model. If you're using, for example, the disk model or some other models, some of these things would be similar results, but maybe a little bit different in the way that they're represented there. So they have some things in common for all four. There are infinitely many points, lines, and planes. Three non-collinear points determine a plane. In a particular plane, there exists a unique perpendicular line to a given line through another point, either on the line or not on the given line. Two proofs are different, but those are characteristics that you could get in all four of these geometries. And we can also visualize all four of these things as embedded in some sort of Euclidean space. So a plane is a Euclidean plane is a plane in Euclidean geometry. If we can think of that as a large flat surface like the top of a table, but it goes on forever, not, up, down, left, and right. A hyperbolic geometry, the points are in an open Euclidean half-plane above the x-axis, at least in the Beltrami-Poincaré half-plane model. The x-axis is not included itself, so basically if you think of these as ordered pairs with the Cartesian coordinate system, all ordered pairs of real numbers will give you points in Euclidean geometry, but only the ones with a positive y-coordinate will give you the points in the hyperbolic geometry. In spherical geometry, a plane, is points on a Euclidean sphere of radius 1 unit. Now, we're mainly thinking of plane geometry when I'm comparing these four geometries, but technically speaking, they all should have multiple dimensions, at least three. In taxicab geometry, uh, the points are just the same as the points in Euclidean plane. Okay, so plane's the same there. How about lines? Well, of course, we have lines or Euclidean lines. Those are what you normally think of as a long, infinitely long, straight object. Uh, Analytically, they have equations in the form ax plus by plus c for some real numbers a, b, and c. In hyperbolic geometry, lines are Euclidean semicircles, open semicircles, By that I mean a semicircle without the endpoints, where the centers are on the half-plane edge, or where the centers and open endpoints are on the half-plane edge, or there's another type that's an open ray perpendicular to and starting on the edge. But of course, all those are things with positive y-coordinates. In spherical geometry, lines are Euclidean great circles. In other words, the intersection of a sphere with the Euclidean plane, which came to center the sphere. They're also circles of radius pi over 2 in the spherical plane. So they're spherical circles and spherical lines. And in taxicab geometry, lines are just Euclidean lines. Any two distinct points determines a line in Euclidean geometry and hyperbolic geometry and taxicab geometry. We have to be a little careful in spherical geometry. Two non-antipodal points determine a unique line. A pair of antipodal points are contained on infinitely many lines. Okay, some things about line segments. Line segment AB is defined to be the set of points consisting of the non-antipodal endpoints AB and all the points between AB. That's the definition. Generally speaking, when we have definitions, the definitions are the same in all the different geometries, and then we just see what the consequence of those definitions give us in the different geometries. In Euclidean, hyperbolic, and spherical geometry, a line segment is the unique shortest path between 2 points, and that is the line segment with those 2 points as endpoints. In taxicab geometry, it is a shortest path, one of infinitely many shortest paths between the 2 points. But it is still a Euclidean line segment. Okay? There are infinitely many paths of the same length that can be created, including many using only horizontal and vertical line segments and others that don't. Line segments are continuous portions of a line, and they can have lengths in the interval from 0 to infinity, not 0 or infinity. That's true in Euclidean and hyperbolic and taxicab geometries. In spherical geometry, line segments are continuous portions of a line, but they have lengths always in the interval from 0 to pi, not including 0, not including pi. In Euclidean geometry, any two distinct points determine a unique line segment with these points as endpoints. That's also true in hyperbolic taxicab geometry. In spherical geometry, you have to make sure that you have the 2 points being non-antipodal pair. So any two distinct non-antipodal points determine a unique line segment with these points as endpoints. How about distance? Well, distance is non-negative and unbounded in Euclidean, hyperbolic, and taxicab geometry, but the formula is a little different. We use the Pythagorean theorem to say the Euclidean distance from A to B is delta x squared plus delta y squared and then square root. Whereas the taxicab distance is the absolute value of delta x plus the absolute value of delta y. A little more complicated formula for the distance in hyperbolic. If you use what's called a cross ratio to measure the distance, so you take basically what you do is you take the line, which is a Euclidean semicircle, okay, you take the points A and B on that, and then take the endpoints M and N, which are on the hyperbolic path plane edge, right? The y equals 0, the x-axis. Okay, remember those are points that make sense in the Euclidean plane, but not as part of the hyperbolic plane. But take them as Euclidean points. Take the Euclidean distance A to M times B to the N, B times N. Sorry, let me say it right. The Euclidean distance from A to M times the Euclidean distance from B to N, divide by the Euclidean distance from A to N times the Euclidean distance from B to M. Then take the log of that and then take the absolute value, and that gives you the hyperbolic distance. See the earlier videos for a better description of that. This is just a summary. If that works if they're not the same first coordinate. If they have the same first coordinate, the formula simplifies a bit, and you get the natural log of the distance from A to M divided by the distance from B to M. Those are Euclidean distances there. M is the point on the edge, right? And then take the absolute value of that, and that gives you that distance. So in spherical geometry, it's a non-negative, but it's bounded to at most pi. That's where we're using a sphere of radius 1. Okay? If we use a sphere of radius 1, then the distance is Euclidean arc length, which is also the angle measure of a central angle intercepting the arc in radians. Think of that as a Euclidean central angle, where if you have the vertex at the center of the sphere as a Euclidean object, and then the sides of the angles then go through the 2 points, measure that angle as a Euclidean angle, which is the same as the arc length along the surface of the sphere. That is it. The radian measure of that arc length is the same as that arc. Radian measure of that central angle is the same as that arc length, and that's the measure of that distance. How about rays? Ray AB is defined to be the union of line segment AB and the set of points C such that B is between A and C. The endpoint of AB, ray AB, is A, and a ray is a half line. So in Euclidean geometry, ray is a half line, has infinite length, continuing forever in one direction but not the other. A taxicab ray is the same thing as a Euclidean ray. A ray is half of a line and hyperbolic as well, and it can be an arc from a circle centered on the edge with the endpoint of the plane and extending to but not including an endpoint on the edge. And it can be, on other possibilities, it can be a vertical Euclidean ray with an endpoint in the half plane and then pointing up, or it can be a vertical Euclidean line segment with an endpoint in the plane and the other endpoint on the edge. So again, see an earlier video for illustrations of all these things. In spherical geometry, we raise a half of a line. Again, it is in all 4 of these geometries. So that makes it a Euclidean semicircle with an included endpoint and a not hang on a second. So it actually has, it's just a Euclidean semicircle, including both endpoints. And one of the endpoints is, well, it's not just any Euclidean semicircle. It's a Euclidean great semicircle, right? Half of a great circle. And both endpoints are included on that. One of them is the endpoint A of the ray, and the other is A prime, the antipodal point. Okay, so it turns out that then ray A B is the same as the ray A prime B. Okay, where A and B are A and A prime are antipodal points. Okay, how about parallel lines? This is one of the main things that's going to separate things. Given a point, given a line and a point not on the line, there exists exactly one line parallel to the given line through the given point. That's the parallel postulate for Euclidean geometry, and taxicab geometry works exactly the same way. But we get a completely different situation in the other 2 geometries. In hyperbolic geometry, given a line, a point not a line, there exist infinitely many lines parallel to the given line through the given point. Whereas in spherical geometry, given a line, a point, a line, there does not exist any line parallel to the given line through the given point. Parallel lines do not exist. How about some things about intersecting lines? 2 distinct coplanar lines may either be parallel or intersect at exactly one point. That's going to be true in Euclidean and taxicab geometry. And guess what? In hyperbolic geometry as well. But in spherical geometry, 2 distinct coplanar lines always intersect in exactly 2 points called antipodal points. So two intersecting lines do not have a common perpendicular line in Euclidean and taxicab and hyperbolic geometry, but two intersecting lines have exactly one common perpendicular line in spherical geometry. Okay, how about some things about angles? Angles in all three geometries are defined to be the union of two rays with a common endpoint called the vertex. Angles have measures from 0 to pi in radians. A zero angle is the same ray twice and has a measure 0. A straight angle forms a line, has a measure pi. Proper angles are neither zero nor straight angles and have measures strictly between 0 and pi. That's all four geometries. So for Euclidean geometry, measure the arc length of the intersection of the interior of the angle with the circle of radius 1 centered at the vertex of the angle to find the radian measure of that angle. Angles in Euclidean and hyperbolic, let's do taxicab next. Angles in taxicab geometry are measured exactly the same as Euclidean angles. In fact, they are Euclidean angles and they have the same measure. So when it comes to angles, taxicab geometry is exactly the same, at least the version of taxicab geometry that we're doing. In hyperbolic geometry, we can draw Euclidean tangent lines to the two hyperbolic lines, or which would be, of course, Euclidean circles or rays, at the vertex and measure the Euclidean angle between these tangent lines to get the measure of the hyperbolic angle. Okay, so it's basically what we would call a conformal measurement because they're measured as you would measure Euclidean angles. Well, how do we measure angles that are curved between the angle between two curves that intersect? Well, we measure the angle between the angle formed by their tangent lines, and that's how we do that in hyperbolic. And essentially, basically do the same thing in spherical. Draw Euclidean tangent lines, which turn out to be in the same tangent plane to the sphere, to the two spherical lines, the Euclidean great circles, at the vertex, and then again measure that as a Euclidean angle between these tangent lines to get this measure of the spherical angle. In other words, we would measure it just as we would measure it in Euclidean geometry. All right, let's talk a little bit about triangles. By definition, three non-collinear points not containing an antipodal pair determine a unique triangle with these 3 points as vertices. Triangles then are a coplanar set of points consisting of 3 line segments with the vertices as endpoints. That's true in all 4 geometries. How about the angle sum? Well, this is where we're going to see some significant differences. The sum of the measures of the interior angles is pi radians, or 180 degrees, in Euclidean geometry, and that's going to be the same for taxicab. In hyperbolic, the sum of the measures of the interior angles of a triangle is always less than pi, strictly less than pi, and the amount that the sum by is less than pi is called the defect. But in spherical geometry, the sum of the measures of the interior angles of a triangle is always greater than pi, and it'll be less than 3 pi, and the amount of the sum is greater than pi is called the excess. So because of this, a triangle can have at most one right or obtuse angle, and 2 of them must be acute for sure, maybe all 3, but at least 2 have to be acute in Euclidean and taxicab, and also in hyperbolic geometry. But a triangle can have up to 3 right or up to 2 obtuse angles in spherical geometry. All right, we spent a lot of time talking about triangle congruence. So the following are enough to determine that the triangles are congruent in Euclidean geometry. Side angle side, SAS, AAS, angle angle side angle, ASA, side side side, SSS, and big S little sa, which is SSA with an extra condition that the side opposite the A, the angle that we know is bigger than the other side that we know. Okay. A special case of that big S little sa would be the hypotenuse leg condition for right triangles. Well, in hyperbolic, it works almost the same way. You have all of those exactly the same, uh, you know, four basic conditions and then the one with the extra condition for the big S little sa. But you also have an AAA condition. Okay, so the angle, angle, angle condition is enough to make it congruent in hyperbolic geometry. In um, spherical geometry, we have most of the same ones, but not all. We do have SAS, ASA, SSS, just like we do in Euclidean and hyperbolic. Like hyperbolic, it has an AAA condition, but the one that's different here is that the AAS is not enough. AAS is sufficient to determine the congruent triangles only if the sides have lengths less than pi over 2. But the really one that's weird when it comes to triangle congruence is taxicab geometry. In taxicab geometry, no three sets of corresponding parts congruent is enough to determine triangle congruence. In fact, the only way you can get congruence other than just showing all 6 parts are congruent is this one right here. We're just missing one angle. The side angle, side angle, side angle condition is enough in taxicab to conclude that the other angle is the other. Um, I'm sorry, I got an extra A there. Side angle, side angle, side, missing one A. That is enough to determine the uh, final angle. But that's the only way that you can get there. Triangle similarity. The angle guarantees triangle similarity. We'll talk about this a little bit more detail in our next chapter. But there are no non-congruent similar triangles because AAA is a requirement for similarity. Similar triangles are triangles which have all the corresponding angle pairs are congruent and the sides are proportional. So the only way to get similar triangles in both both hyperbolic and spherical geometry is that they have to be congruent. So really nothing, the similar triangles doesn't really apply there. AA does not guarantee congruence triangle similarity, but there are some non-congruent similar triangles that exist over here in taxicab geometry. All right, how about a couple things about circles? Circles are defined to be the set of points in a plane which are an equal distance called the radius from a given point called the center. Circles have a unique center and radius. Well, that's not exactly true. That's true. Let me fix that. So circles have a unique center and radius. That's true for Euclidean, hyperbolic, and taxicab geometry. But in spherical geometry, when you have a circle, it's a set of points there. You can think of it has a center point and a radius. So if it has a center point A and a radius R, then you get the same circle if you take the center point being the antipodal point A prime with a radius of pi minus r. So they have two center radius pairs for that geometry. The circumference of a circle divided by its diameter is an irrational constant we call pi. That's true in Euclidean geometry. However, in taxicab geometry, the circumference of a circle divided by its diameter is a rational constant, 4. Circumference of a circle divided by its diameter is variable for spherical geometry, and it's somewhere in the interval from 2 to pi, including 2 but not pi. And in hyperbolic geometry, the circumference of a circle divided by its diameter is variable, It's always greater than pi. It approaches pi as the radius approaches 0. And we have this relationship here with the hyperbolic trig function there. In Euclidean geometry, of course, circles are Euclidean circles. If we did that analytically, it would be set of points with the coordinates x minus h squared plus y minus k squared equals r squared, and that's a circle centered at the point hk with radius r. And in hyperbolic geometry, circles are Euclidean circles, but with the center directly below the center of the Euclidean circle. And circles in spherical geometry are Euclidean circles, and the radius is in the interval from 0 to pi. Circles in taxicab geometry are Euclidean squares with sides at an angle of plus or minus pi over 4 with the horizontal, 45 degrees plus or minus. A circle at center HK will have, with radius r, will have the equation x minus h absolute value plus y minus k absolute value equals r. How about polygons? The minimum number of sides of a polygon is 3 in all 4 cases. However, notice that that an angle is a closed plane figure made up of 2 parts of 2 lines. Some people call that a digon. I just call it an angle, but that is not a polygon by our definition. The class of quadrilaterals ABCD with triangle ABC congruent to triangle ADC is the same as the class of kites. And that's true in Euclidean, hyperbolic, and spherical geometry. It's a subset of the proper subset of the set of kites in taxicab geometry. The class of quadrilaterals ABCD with triangle ABC congruent to triangle DCA is the same as the class of parallelograms in Euclidean geometry, but that class is a proper subset of the class of parallelograms in hyperbolic, and that class exists in spherical geometries, but trapezoids and parallelograms do not exist there. And in taxicab, once again, that class is a non-empty intersection with the class of parallelograms, but neither is a subset of the other. Equal angular quadrilaterals, rectangles, have 4 right angles in Euclidean geometry. In hyperbolic, equal angular quadrilaterals have 4 acute angles. I would still call those rectangles by our definition. They could have various measures of angles there. And they could have various measures of angles in spherical geometry as well, but they'll all be 4 obtuse angles. Taxicab geometry, equal angular quadrilaterals have 4 right angles. So taxicab rectangles are Euclidean rectangles. If we let A, B, and C be the measures of the interior angles of triangle, and little b, and little c be the lengths of the sides opposite these angles, respectively, then we get some trigonometry. So we'll talk about this a little bit more later. This is stuff that we haven't really talked about so far in the notes, but I thought it'd be a good place to put it here for reference, and we may or may not get back to some of this stuff. So if C is pi over 2, a right angle, then we get A plus B is pi over 2, so those are complementary angles. The sine of angle A is little a over C, sine of angle B is little b over C, and so forth. So you get the basic trig functions get up here. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent's opposite over adjacent. For any C, we can extend this. We have the angle sum theorem, A plus B plus C. Those measures of the angles add up to pi radians or 180 degrees. We also have an extension of the Pythagorean theorem called the law of cosines that says little c squared equals a squared plus b squared minus 2ab times cosine of the angle C. And we have something called the law of sines that says little a over sine of angle A is equal to little side B, length of side B over the sine of the size of angle B equals C over sine of big C. So using the law of sines and law of cosines, we can, for all the cases where there's one congruence class of triangles, we can solve for it. In fact, we can solve for all of them, even in the cases where there's more than one. If there's an ambiguous case of the SSA, we can solve for both of the two congruence classes. If we're in the AA situation, we could just pick, say, a side of 1, solve for that, and then all other ones are similar, and so that we get not one, but infinitely many congruence classes there, but we can find out what they are. There's also, for taxicab geometry, we still get the angle sum theorem, but the sides, it's really hard to come up with any kind of trigonometry there for the sides because it's very different. It turns out there are some trigonometry for hyperbolic here and spherical geometry over here, and I'm going to just leave those there without a lot of explanation at this point, but it's just there for reference if you want to come back to it later. Finally, I want to mention that in the past couple of sections and related homework sets, we introduced the Euclidean parallel postulate. Since introducing the parallel postulate, the Euclidean version, we have been primarily focusing on Euclidean geometry with some occasional references to spherical and hyperbolic geometries along the way. We pretty much abandoned taxicab geometry back when we were talking about triangle congruence, or after we talked about that, once we introduced the SAS postulate. In particular, the transversal to parallel lines theorem with the included Z, C, and F properties turned out to be an important set of results and excellent tools for use in proving other propositions. And so much of our work over the last few homework sets, the last few chapters, the last few videos, was focused on classifying quadrilaterals and determining properties of various subclasses of quadrilaterals. Some of these proofs for these made use of the triangle congruence postulate, the SAS postulate, and the theorems like angle, angle, side, angle, and side, side, side theorems, triangle congruence theorems. But they also made use of the Z, C, and F properties from this transversal to parallel lines theorem. And those were our important main tools for doing that. So at this point, you should be very comfortable with writing proofs about quadrilateral properties, at least in Euclidean geometry. For those of you going on to teach high school geometry, you should also expect your high school students to produce good proofs. So if you're a high school student watching this, I would expect you to be able to do some good proofs of some basic things in here. For example, you should definitely be able to do things like prove that a quadrilateral is a parallelogram if and only if it has a pair of opposite sides that are congruent. Those sorts of proofs are really good for high school students and definitely a core thing that both a high school and college geometry students should be able to do. Now, really from this point on, we're going to be nearly exclusively focusing on Euclidean geometry. We're only going to occasionally make reference to the other geometries. So we've gradually been kind of pulling away from these others. Again, we mainly used taxicab geometry to show us that the SAS postulate, side angle side postulate for congruence of triangles is independent of the other postulates. And we see that triangle congruence works very differently in taxicab geometry. So once we introduce that postulate, then we pretty much quit talking about taxicab geometry for the most part. The big thing historically when we introduce the parallel postulate is to notice that it's independent of the others, and the existence of hyperbolic geometry in particular, and really spherical geometry as well, but especially hyperbolic geometry, shows us that postulate, the Euclidean parallel postulate, is independent of the other postulates. And so now that we've done that, we will mostly, hyperbolic geometry has mainly served its purpose for our study this semester, and same for spherical, so we'll start to kind of go away from those as well. In particular, our next unit is on Our next little chapter is on similarity and some concepts of that. And similar triangles that are not congruent don't exist in hyperbolic and spherical geometry. So another reason there for abandoning those two geometries in our further study. So um, good news or bad news, I'm not sure, but for the rest of the semester, we're going to pretty much be focusing on Euclidean geometry almost completely 100% exclusively, maybe just a few side mentions of the others. But hopefully this geometry lecture here gives you a good summary of a lot of the things that we've seen about the different geometries and how they kind of compare side by side.